Hey everyone, this is a video about heterogeneous equilibria. Everything we've studied up until this date in these videos has been substances where the reaction species have all been in the same state of matter. I think they were all gas up until this point, or perhaps all aqueous solutions. But in the situation where you have a heterogeneous equilibria, where you have substances that are in different states, for example, calcium carbonate can decompose and give you calcium oxide and carbon dioxide gas. This is considered a heterogeneous equilibria because while these two guys are solid, the carbon dioxide is a gas, so they're in different states. One would think that you would write the equilibrium expression like this, where you take the products divided by the reactant, calcium carbonate in this instance, but that is incorrect. In fact, we don't include the calcium oxide or the calcium carbonate, and that's because it's in the solid state. And if you really think about it, these substances that are in solid states, when they undergo a reaction such as this, they're not actually changing concentration. So for example, let's assume this is the calcium carbonate right here. If the calcium carbonate is decomposing and carbon dioxide gas is coming off this, and some of the solid remains is calcium sulfate, this solid block of calcium carbonate may be decreasing in the number of calcium carbonate molecules over time, but it itself is not changing concentration or density. I mean, even if calcium oxide is what's being, is a solid that's being left behind, the part of it that is the calcium carbonate, right, the original purple here, its concentration is not changing. Its density is not changing. It may be getting smaller, parts of it may be breaking off, but because its concentration is not changing over time, we don't include it in the equilibrium expression. Same is true for the calcium oxide. As this part of it grows, and as the calcium oxide, appears here and deposits, it itself is just growing in mass, but the density of what's growing is not changing, and nor is its concentration. So because the concentration of solid species does not change, just their amount, then we do not include them in the equilibrium expression. So the equilibrium expression for this particular reaction is simply the concentration of the CO2 gas. Let's take another example. If something is changing and instead of solid, we have liquid. So if, let's say, substance X is a solid, and this produces substance Y, a pure liquid, and substance Z, a gas. Again, one would expect that we would write the equilibrium concentration, or the equilibrium expression, Y times Z over X, but this would not be true. Again, because we have a solid substance, this does not appear in the equilibrium expression, and if you have something that is a pure liquid, that also does not appear in the equilibrium expression. The equilibrium expression for this is just simply the concentration of Z. Again, if you think about this, the appearance of, in this case, a liquid is a pure substance, just like solid is a pure substance, and so while the liquid may grow in volume over time, because it is a pure substance, its concentration is not changing. The term concentration really only refers to, one part of a mixture. And in this case, we have the gas concentration will and can be changing. So anytime you see a liquid or a solid in an equilibrium expression, we do not include those species in the in the equilibrium expression.